So how do we identify these null and alternative hypotheses? Um, there are literally dozens of ways that this can be done. I have seen so many of them. I've taught so many of them. The process that I'm going to outline is the one that I think is the simplest. And it's going to work a little bit different than the next video is, which is going to be a little bit different than the next video might be, right? By different people, not by me. And if you find a way you like that's a little bit different, a tutor explains it different, our previous teachers explained it differently, that's okay. There are lots of different ways this can be done. You just need to find something that works for you. The way I'm going to explain it is the way that I think is the easiest to keep it straight and not make a mistake somewhere. But understand if you go get help somewhere else and they describe it and work it out a little bit differently, that's okay. There's not just one right way to do this. Okay, so the way I'm going to explain it is I'm going to start off and I'm going to say our first step is going to be to write the claim in symbol form. And so what I mean by that is we're going to start off with some claim that's going to say the majority of people do not support, or the majority of people do not support this new proposal we talked about in the initial example. And that's a claim in words, but we've got to write it in symbols. All of our claims in symbol form are going to have three pieces. In this chapter here, we're going to have claims that have three pieces. They're going to start off with a parameter because every hypothesis has to have a parameter. It's going to have some mathematical operator that's either equals, greater than or equal to, less than or equal to, less than, greater than, or not equal to, right? So some form of like, it equals this, it's less than this, it's whatever, right? And then the third piece is it's going to have some number, okay? So in my example here, a majority of people do not support this claim. Notice I didn't give you a number, but I gave you majority, which ought to tell you 50%, right? Now, of course, we don't work in percent, we work in decimals, so 0.5, right? So we're either going to be given a number or we'll be able to infer a number. So in that example, majority of all people do not support this claim. My claim would be, P is less than 0.5. And so boom, I've got a claim and I've got it in symbol form again, three pieces, some parameter, some mathematical operator, and some number. Now, if the claim is directional, and what I mean by a directional claim is it's got a greater than or a less than in it. So greater than or equal to, less than or equal to. The alternative hypothesis is the same symbol, but without equality. So if it doesn't have equality to start with, then the alternative hypothesis is just the same thing as the claim was. If it does have equality, we're just going to drop that equal. Okay. Now we're going to list out our null hypothesis first when we formally write this up. I like to find the alternative first. Okay, so just make sure you catch that I like to find the alternative first. Again, that's just my preferred method. But when we write out our hypotheses, we're always going to write the null first and the alternative second. Okay. So this is how to find the alternative hypothesis. If our claim is directional, then the alternative is the same symbol but without the equality. If the claim is not directional, which means equals or not equal, then the alternative hypothesis is not equal. And so as we've kind of talked about, I've listed them out several times, but I want to make sure you're on the same page here. There are only 6 different options for your claim. Your 6 options for your claim are, for the mathematical operator claim, are equals, not equals, greater than, less than, greater than or equal to, or less than or equal to. Now make sure you understand the claim doesn't start with those. The claim starts with a parameter, right? So you got to get that out of the way first, right? Are we, population what, right? Population mean, population standard deviation, population proportion, right? What is the parameter, right? So we have a parameter, we have a mathematical operator. That's what I'm talking about here. There are 6 options that you have and then some number, okay? Of these 6 options, note I've listed them out, all of your options. 4 of them go in that second bullet point. The greater than or equal to, less than or equal to, all fall in that second bullet point. If you're in one of those boats, then the alternative is that same direction, but just without the equality. Your last 2 options are equal to or not equal to, and if that's the case, then your alternative is not equal to. Once you found the alternative, it's downhill from there because the null hypothesis is just the opposite. And by opposite, again, we mean the idea of a complement, right? If you have a greater than alternative, the opposite of that is less than or equal to, right? We have to change the direction and we have to include the or equal to because we didn't have it before. The null is always going to have an equality, the alternative will not. And then a little note here, Some textbooks teach that the null should be equal to all the time, no matter what. That's fine too if you want to write it out that way. That's not a big deal if it makes your life simpler. It's more technically correct to write the null as the opposite of the alternative. So if your alternative is greater than, then the null would be less than or equal to. If the alternative is less than, your null would be greater than or equal to. But again, some textbooks will just say, nah, just make the null equal to no matter what. There are reasons for that. We don't need to dive into them now. That's more advanced as to why one is preferred over the other. Okay. And so let's look at some examples. Identify the hypothesis for the claim that the actual average IQ of students in this university is 100. So first off, okay, we know that we have to identify some parameter. How do I know what parameter? First off, how do I confirm that? Well, notice you see the word actual, right? Anytime we see the words all, real, known, true, actual, these are all population words, okay? So we know that we have a parameter, which we already knew that from the start, that the claim has to involve a parameter. And then we can see that we have the word average. And so that leads me to believe that my parameter is going to be mu. That's the first part of the three from my claim. And then I have to figure out what symbol, what mathematical operator goes with that parameter. And then what number? Clearly the number is 100, and so then I've just got to figure out what symbol. And of course, we know that in math, the word is means equal. So my claim is that mu equals 100. Now I want to make sure as we go through these, we understand that the claim is not always the null. The claim is not always the alternative. Sometimes it's one, sometimes it's the other, sometimes it's neither. Okay, so I'm going to say that this claim is that mu equals 100, and I'm only using the claim to find the null and the alternative. Make sure you understand that. Very key idea. We are only using the claim to get the null and the alternative. Once I've got the null and the alternative, I literally don't care about the claim anymore. You can just cross through it with a pen if you want. We will not touch it. We do not want to touch it. We want to ignore it because everything that we need to know is on the null and the alternative, because that's how the test is based. The claim is just a means to an end. It's just to get us to what the null and the alternative is. I could care less what the claim is once I have a null and alternative. Okay. And so my claim is that mu equals 100. And so I just go to the top of the page. My little worksheet here. How do I figure out what the alternative is? And we're going to find that one first. Notice that third bullet point says if this claim is equal to or not equal to. Oh, we're in that boat, then the alternative is not equal to. So I know that my alternative is mu not equal to 100. And then the null is just the opposite. So if my alternative is a not equal to symbol, then my null is an equal to symbol. Again, make sure, remember, we have three parts to it. You don't just say, oh, the null's not equal to 100. The alternative is not equal to 100 and the null is equal to 100. It's what is not equal to 100. What is equal to 100? So we can talk about it colloquially, but make sure when we write it down, we write down all three pieces. Okay, so here would be our hypotheses. So again, we may just word it out and just talk about where the equal to, where the not equal to goes, because that's what's interesting here, right? About making sure that we get these together correctly. But when we write it out, we don't want to leave out the parameter here in front of those symbols. Again, we write the null first, the alternative second, even though we find the alternative first. Next example, identify each hypothesis for the claim that the actual average IQ of students in this university is not 100. And so now, same thing, actual average, okay, that's mu. The number's 100. What operator goes in between them is not, would be not equal to. And so my claim is a not equal to claim. And so again, back to that worksheet at the top, the third bullet point again, and it's the same alternative. Right? If the claim is equal to or not equal to, the alternative hypothesis is not equal to. So two different claims led me to the same alternative and thus the same null, because the null just builds off of whatever happened with the alternative. So we have the same hypotheses here. So again, notice in this case, the first case, the claim was the null. The second case, the claim is the alternative. This is why we say ignore what the claim is. It doesn't have to be one or the other. We never want to force it to one or the other. Once we get the hypothesis, we just do not even care anymore about that claim. We don't even care that it's the null or the alternative, right? We're just going to completely discard it. We have everything we need for these hypotheses. Next one, identify the hypotheses for the claim that the actual average IQ, so still mu, students in this university is greater than 100. So now we're off that third bullet point on that little worksheet up at the top of this page of how we work through finding these hypotheses. And my claim is a greater than claim. So I might want to write that down. I don't have it here on the slide, but I might want to make a little note to the side, right? Claim is mu greater than 100, right? You may want to write that out, may help you. If not, that's fine, may help you out. So that second bullet point says if the claim is directional, this is a directional claim, right? Anything think about like a number line, right? If I would shade it one way or the other, right? That's directional. Claim is mu greater than 100. The alternative hypothesis is the same symbol, so same direction, right? So we don't flip the greater than less than, right? If it's going to the right, we still go to the right. If it's going to the left, we still go to the left. So we're still greater than, but without the equality. Oh, this one didn't have an equality to start with, so we just get to write that down. We don't have to change anything. So my claim in this case is the alternative because I don't have to remove an or equal to because my claim didn't have an or equal to. And thus my null is just the opposite of that, right? Same parameter, same number, but now my symbol is the exact opposite. So I need to flip the direction and then I need to add an or equal to, which lead me to these hypotheses. And then in my last one, we have the claim that the actual average IQ, again, mu of the students in this university is at least 100. The at least translates to greater than or equal to. So again, if you're a little fuzzy on that, make sure you're fresh on at least, at most, greater than, less than, how we get those into symbols. Okay, so again, if you want to write out to the side, claim is mu greater than or equal to 100. Go back to my worksheet at the top. That's a directional claim. The alternative is the same symbol, but without the equality. So that means I want to take greater than or equal to, and I want to drop the or equal to, and I want to make that alternative just greater than. So my null and alternative are going to be the exact same as we had before. And notice in this case, the claim greater than or equal to, mu greater than or equal to 100 is actually neither the null or the alternative, which again illustrates the point. The claim is sometimes the null, sometimes the alternative, sometimes neither. Okay, we don't really care. It's just a means to an end. Once we have these nulls and alternatives, we are good to go. And of course, just note, while we only did examples here using mu, the same thing would hold true for any parameter, whether that's p, sigma, sigma squared, right? Any population value, the same thing applies, right? We could take this last example and it could say identify the hypotheses for the claim that the actual variance of IQs of students in this university is at least, I don't even know what would be a reasonable variance. We'll call it 100, doesn't even matter, right? And it'd be the same thing, except instead of having mu, I would have sigma squared, right? Because that would be the symbol for the population variance. So it applies no matter what the parameter happens to be. Also take note in these examples that we did here that the first two examples would be considered two-tailed tests, okay? The last two examples would be considered one-tailed test. And if you wanted to be even more specific, it would be right-tailed test. That is because we identify what type of test we have based off of the alternative hypothesis. And it's basically, where would we shade? Where do we think the alternative could be? Notice in these last two examples, again, we'll call these right-tailed tests. It means that based off the alternative, that the true value of this mean, that this mu could be off to the right. It could be 105. It could be 110. It could be 120. We're going to the right on a number line, right? We are not going to the left. We don't think it could be less than that, right? The alternative, again, the research hypothesis, what am I researching? What do I think could happen, right? I don't really think that mu could be that small. I'm thinking research-wise, mu might be large, right? It might be off in that one tail. That's why it's called a one-tailed test, right? And again, more specifically, a right-tailed test because which one direction am I going? I'm going to the right. I'm going greater than. Those first two examples we call two-tailed tests because my alternative just says mu not equal to 100. Notice if I say, again, research hypothesis is what do I think it, alternative hypothesis, research hypothesis, what do I think it could be, right? In these two examples, I'm thinking it could be greater than 100, but in my first two examples, I'm saying mu not equal to 100. I'm saying, I don't really know. It could be greater, it could be less. By saying mu not equal to 100, I'm saying, I don't really know where it is. So that's a two-tailed test because it could be to the right and it could be to the left. And so that's how we're going to label what type of test we're working with, right? So that's just going to be some, vernacular that we're going to use throughout this chapter.